Start recording it. Cool. Okay, welcome everyone to chapter 2 of the post-Bayesian series. We're going to be carrying out chapter 2 for about 2 months. So from today until mid-July, then we'll have a nice little summer break before we move on to part 3. Of course, I'd like to thank the organizers again for their great work, especially to Jan and Matthias for a lot of the organizational work. As before, we have kind of the list of important links. So please do sign up on the website if you'd like to be part of the mailing list, calendar, etc., just so you can have access to all the talk links. And please continue to share this widely. Just a little bit of advertisement. We'll be participating in a satellite workshop at BayesConf on Bayesian computation and inference with misspecified models. Jeremiah will be giving one of the talks, as will I. So it'll be quite fun to meet some of you there and talk about this in person if you can make it all the way out to Singapore. As with the previous talks, we'll have this kind of question and comment section. Basically, you can use the Q&A function in Zoom. Jan and Matthias have kindly offered to monitor it, so they can stop me if they'd like. Also, please feel free to interrupt me during the talk if there's any questions in the middle. Jan and Matthias will keep an eye out on the chat. Otherwise, we can kind of go through it at the end. I'll try to leave some time. Okay, so with all the administrative things out of the way, I just wanted to start with a brief recap, basically stealing Jeremiah's slides from his first chapter. The main idea behind the post-Bayesian seminar is that kind of the modern Bayesian is a little bit ill-equipped to deal with some of these problems that we're facing today. So Bayesian inference, as we all know, operates on some pretty stringent assumptions. The first is that the model or the likelihood is usually assumed to be well specified. The second is that the prior distribution kind of represents the world quite well, or you have some way of constructing a prior. And the final assumption is that computation is actually feasible for the posterior. And of course, as alluded to in all the previous talks, this is a pretty fragile set of assumptions. So in modern big data settings, it's not so easy to specify correct models, nor is it easy to specify priors that don't impact your inference negatively. And of course, we all know computation for Bayes can be a nightmare. So today we're going to be talking about kind of a way to basically relax all three, because we won't even have a model or a prior. Interestingly, we can still compute the posterior, so that's a little bit of a teaser for things to come. So Jeremiah's covered nicely chapter 1, which was looking at treating Bayes as an optimization problem, which gave you things like the Gibbs posteriors or Cole posteriors. I'll be covering chapter 2, so I'm giving today's introduction talk. My name is Edwin, and I'm an assistant professor at HKU. I was a PhD student with Chris, so it was really nice to be kind of part of the transition between Gen Bayes and this martingale posterior or predictive Bayes type work, like literally during the time I was doing my PhD. Then after chapter 2, there'll be a quick summer break, and then Professor Pia Akel will take on with PackBase after the summer break. So those dates will be updated soon. We've got an exciting set of speakers lined up. There's fewer speakers than the first chapter because kind of predictive Bayes, at least in its modern form, is a little bit newer than Gen Bayes, so there's fewer people working on it. But in 2 weeks' time, I'm really fortunate to invite Professor Sandra Fortini from Bocconi University to talk about theoretical foundations of predictive Bayes. Most of her work has been inspirational for me during my PhD with Professor Sonia Petrone. 2 weeks after that, we'll have Rick Schreiber, who's a PhD student with Chris Holmes, talking about predictive model selection and uncertainty. So thinking about how to choose between models in a purely predictive kind of way, as well as kind of thinking of replacements for Bayes factors. We'll have a 2-week break because many of us will be at BayesConf or BNP. And then on July 1st, we'll have Professor Lorenzo Capello, who will be talking about some specific kind of methodology related to these kind of recursive methods, which are useful for predictive Bayes. Again, like super interesting work that kind of moves quite far beyond the traditional likelihood and prior Bayes methods. And then finally, we will have a joint session by Dr. Harita Della Porta and Matthias, who's one of the organizers, where they'll be talking about some of the applications of post-Bayesian methods. So it'll be kind of a fusion of chapters 1 and 2. Harita will talk a little bit about applications of the Bayesian bootstrap. Matthias will be talking about applications of the generalized posterior, and you can kind of see, at least get a glimpse of how these tools will be used in practice. Okay, so without further ado, we'll get started with the kind of technical part of the talk. You can see my transition to Beamer slides, which indicates that things are about to get a little bit more statistical. I do promise there are figures in this talk. There's even an animation, believe it or not, although it's the same animation I've used for many years now. So I'm going to be giving an introduction, a little bit of history and an overview of this kind of big umbrella topic of predictive Bayes. I'll be talking more from some of the work that I've done because I'm more comfortable with that. I know that in 2 weeks' time, Sandra will give an amazing kind of overview of her theoretical contributions. So to start off, we're going to cover introduction and talk a little bit about what predictive Bayes really is in a nutshell, how it kind of changes the viewpoint to regular Bayes. And I also want to highlight that actually this is not really a new idea. There's a huge history. And it's only kind of recently that this has been revitalized, so to speak. I'll talk a little bit about an algorithm that we coined as predictive resampling, but it's kind of just really imputation. It's been spoken about before as well. And then at the end, I'll kind of go through a parametric example, a parametric Bayesian example, which shows that you can actually kind of do this in practice. So if there's anything to take home from today's talk, hopefully it'll be the parametric example, which will make sense. Okay, so traditional Bayes in a nutshell, this is not new for anyone, but I think it's quite helpful to kind of delineate, at least in my opinion, which parts are Bayesian and which parts are kind of predictive Bayesian. So the traditional Bayesian tends to specify a sampling density or likelihood, and then a prior distribution on their parameter of interest theta. So we saw earlier in the Gen Bayes chapter 1, you replace the likelihood with something based on the loss function, but you retain the prior distribution. And basically just from specifying these two things alone, you can do basically all of statistical inference. So you can carry out parameter inference, you can use Bayes' rule to get the posterior, you can do marginals, you can do model selection, so you can integrate over the prior, get the marginal likelihood. And finally, you can also do prediction. So you firstly compute the posterior and then you integrate that over the likelihood. But what I want to highlight in the slide is that there's a strong focus on probability measures on theta, even in generalized Bayes, that you put a prior on theta and you talk about how it connects to the data. So the posterior is really just the prior, but updated, so I kind of put it in the same boat. The predictive Bayesian approach actually kind of flips things around a little bit, but you can end up doing the same three tasks: parameter inference, model selection, and prediction. And as a predictive Bayesian, my kind of philosophy is to specify the predicted density directly as my model. So here, n is just an arbitrary index. It doesn't have to be like a single data point. In fact, it's usually going to be a sequence of predictive densities. And that's going to be the place where I start. So not the end product, but instead the place that I start. And what we're going to show you today and throughout the rest of chapter 2 is that you can actually do all of Bayesian inference with just that. So obviously the most interesting part for me, and kind of most difficult at least, is that you can actually use this predictive density to do parameter inference. So we're going to be talking a little bit about kind of an algorithmic way to do this today, but long story short, you can use these predictive distributions to essentially do a kind of bootstrap. So we'll talk a lot more about this in detail, but the idea is that this is the same thing as doing posterior sampling. Notice that there's no kind of pi of thetas anywhere. You can also use this for model selection. This one's a little bit more obvious, but this has really rich history as well in the model selection literature, which is that you can construct the marginal likelihood as a product of sequence of predictives. So again, here, there's no kind of pi of theta anywhere. And actually, the final point is a little bit subtle, and I think is really interesting. I'm not an expert in this, but there are cases where choosing the predictive actually lets you kind of work backwards to get the likelihood and the prior that's implied. So this is some of the work that Sonia and Sandra have done, which is like super interesting, which sort of means that actually, if I start with the predictive as a predictive Bayesian, I actually kind of have the full picture already. I'm not really missing anything. And so today's talk will be showing you how this is formalized, especially sections 1. Sections 2 will be kind of covered more by Vic in the later talk. And then we'll talk a little bit about what this implies for statistics and what kind of new methodology can come out of this. How is this post-Bayesian? Okay, so a little bit of kind of hand-wavy discussion about why we would want to do this in the first place. Why is working with the predictive directly desirable? And there's kind of a lot of different reasons, but I think one of the ones that's most exciting for me is that we've gotten pretty good at eliciting predictive distributions directly. So with things like machine learning, where the parameters that you're kind of estimating don't really mean anything in terms of statistics. You just basically have a black box density estimator, so to speak. There is some caveats about this kind of interpretation, like this is the reason why I'm really interested in it, but actually putting this into practice, we'll talk a little bit about later. The second point that Chris mentioned a lot during my PhD was that he really liked predictive statements because they can be validated. So what validated means is that I can observe data in practice, so I can actually test if my predictive model is good or not. Whereas probability statements on theta, like a prior or even a posterior, it's pretty hard to validate outside of simulations because you'll never actually see theta in practice. It's an unobservable quantity. So in a sense, it's really nice that you can actually just specify your statistical model in a way that's completely tied to the real world. Of course, there are also some caveats with this interpretation. It's not quite true that you can't evaluate your prior. For example, the things like the marginal likelihood exist, but kind of on paper, it's nice to talk about things that exist. And interestingly, which is kind of one of the other reasons why I'm really interested in the predictive approach is sometimes computation can be much more expedient, like way easier. In fact, for most of these kind of predictive approaches, because you specify the model directly, you don't need to do MCMC. The kind of sampling schemes sometimes are a little bit weird, but at least in practice, we've seen that tends to be orders of magnitude faster. Okay, so how do we actually connect the predictive to the posterior? I think that's kind of the place that we want to start with. But before we move on to actually constructing this joint predictive, I think it's really important to pay homage to the proper history. And predictive Bayes has a really long history. I think it's really easy to forget, but actually all the way back to De Finetti. So this is the seminal paper by De Finetti, more of like a bunch of chapters than a paper, is really long. And of course, the original version is not in English, but the translated version is pretty readable. And I think everyone's familiar with De Finetti's representation theorem. The philosophy behind this is that if you have an exchangeable sequence, so you have some subjective probability distribution that's exchangeable, infinitely exchangeable on your observations, then underlying this is kind of this hidden Bayesian process. You have this marginalization of the likelihood over the prior. I mean, everyone kind of is familiar with this part. The kind of undertone is already clearly there, right? That probability statements on data can have kind of implicit probability statements on parameters. But I think the kind of underrepresented part of De Finetti's theorem is on the next slide. This is in the original paper as well, but it seems to be kind of underplayed compared to the representation result, which is that if you take this exchangeable sequence, right? So it's a probability measure, and imagine drawing samples, y1 to n from it, and you take the average of those samples, as you construct a longer and longer sequence of infinitely exchangeable random variables, it actually converges to a sample from your prior. So this kind of connection means that I can talk about the parameter and the distribution on the parameter as a purely kind of data-driven thing. Like this object doesn't talk about the prior or the parameter. It doesn't exist. But I kind of have this push forward of the sample, which then actually comes from the prior. And indeed, this even holds conditional on data. There's an insightful excerpt from Bernardo and Smith, which is also sort of underappreciated, which is that if I have a binary sequence, I can actually look at the limiting predictive distribution and now be exactly the same as the posterior. So don't worry if this kind of goes over your head for now, because we're going to talk about this in a lot of detail. But kind of the ingredients were already there. Actually, historically, the reason why people turned to using the likelihood in the prior was because it was pretty darn difficult to construct these big joint predictive distributions that were exchangeable. So De Finetti opted to use the likelihood in prior to actually construct this. But fortunately today, many, many years later, we can actually directly go for the predictive. So in between De Finetti, there's been a lot of kind of other people who have been really interested in the predictive approach. Just going to mention a few of my favorites, but of course, this kind of goes back a long time. One strong proponent of the predictive approach was Phil David. So he coined this term prequential, which is predictive sequential. Vic is going to talk a lot about this in a month's time, and also Seymour Geisser. And so they were really concerned with kind of using prediction as a token for doing model selection. And Seymour Geisser even spoke a little bit about doing inference in this case. So they're all kind of precursors, but nothing really kind of took off after the introduction of these methods until a recent resurgence in interest. So I would say that the paper that really kind of kickstarted it all was this paper by Sandra Fortini and Sonia Petroni and J.R. Speak, so quasi-Bayes properties of a procedure for sequential learning and mixture models. This paper was kind of like the thing that I was using to learn about the predictive approach. So in this work, they introduced basically a likelihood and prior free version of Bayesian inference, specializing with the non-parametric mixture model. So there's this kind of recursive update called Newton's method that I think Lorenzo or Sandra will talk about later on. And around the same time, there's a paper out by these wonderful people called like Bertie and al. So Rigo is kind of the one who's driven all of this. They've done a lot of work on the theory underlying these kind of martingale-like sequences, which again, Sandra will talk a little bit, hence the icon on the top right. And then recently, some work with me and my PhD supervisors have sort of put this into a more parametric framework, so to speak. So we introduced this notion of martingale posterior distributions, but really it's just kind of a packaged version of some previous ideas, but we focus much more on the parameter case, which I guess is more kind of in line with the post-Bayesian methodology. But this is kind of why I would say these are the main three papers that sort of kick things off, so to speak. And now there's a lot of people working on related methodology, so it's quite an exciting time. But it's still relatively young. You can see the first paper came out in 2020, so we still have a lot to kind of catch up on with respect to generalized Bayes. So I've kind of teased this notion of being able to do posterior sampling using a bootstrap-like approach, and now we're going to kind of dig into it. I think there's some nice philosophy behind it as well. So I have a couple of philosophical slides in the middle, and then we'll talk a little bit more about methodology. So the statement that Stephen likes to kind of start with, so Stephen Walker was one of the other co-authors, he always talks about how statistical uncertainty, like where does statistical uncertainty come from? So I think both Bayesians and frequentists can agree that when you see a finite sample y1 to n, the fact that it's finite is why there's any uncertainty to begin with. So if you had access to the whole population, which we kind of write informally as y1 to infinity, you can think of this as being able to draw an infinite number of samples from some distribution f, then technically you would know any parameter of interest as long as it's measurable. So you can just kind of take an infinite number of sample and compute the mean, and voila, you have the mean. So the predictive approach is actually to basically look at that remainder of the population as the source of uncertainty. So we've seen y1 to n, we haven't seen yn plus 1 to infinity, so why don't we talk about our kind of subjective uncertainty in this remainder of the population? Turns out if you kind of take this to the extreme and actually do this for sampling, you get a pretty interesting kind of bootstrap-like scheme. So conditioned on your data, suppose you had access to this joint predictive density. We're going to talk more about how to construct this, but for now, you can just imagine this coming from your Bayesian model. So the posterior predictive over kind of the remainder of the population. Suppose you had a way of drawing samples from this, yn plus 1 to infinity. Yeah, it's a little bit heinous to draw this infinite sample. We'll talk more about that later as well. But given this imputed population, you can obviously just compute your parameter of interest theta because you've seen everything. So it's just a deterministic map. And because yn plus 1 to infinity is random and conditioned on y1 to n, theta infinity will also be random. You'll have some distribution, again, conditioned on y1 to n. And it's no coincidence that you can show using multitude of different methods, but the way that we opted for was using Dub's martingale kind of type arguments. You can show that if you construct this using a Bayesian model, so I construct this joint from my Bayesian posterior predictives, and I estimate the parameter as, say, my maximum likelihood estimate, you do actually get back the posterior, like it's equivalent. So I didn't actually need to talk about the prior or the posterior to actually get samples from it, which I think is pretty neat. Sort of on a philosophical level, my supervisors like to talk about kind of the Bayesian imputing what they need to know the parameter. So you want to know yn plus 1 to infinity because you're interested in theta y1 to infinity. So why don't you just impute that? Of course, this is not a very easy task. It's actually kind of the biggest problem right now. But you can actually do this in practice. So we're going to show you later on a little parametric example where both of these guys are very easy to understand and come from a parametric Bayesian model. And you can see with simulations that indeed this statement holds true. Also a little bit about the intuition. Okay, so here's a little visualization we can do. It's easier to think about things in terms of a finite population. The argument actually extends to the infinite case using kind of careful theory. So suppose I had a population of size capital N, and I managed to obtain 2 samples. Since it's IID sampling, I can kind of reshuffle the indexing. So the first 2 people, or so to speak, are the things that I've seen. If my parameter of interest is some functional of the population, maybe let's say I want to calculate the column of mean A, then what you can do to get a posterior distribution is to first fill in the remainder of the table. So you're going to fill in the remainder of the table conditioned on the first 2 people using some kind of predictive machine. And then after that, given the imputed table, you can just compute the average of column A. Like no tricks. You just take an average of column A, and that's going to give you a random value for the column A. And you do it again, you get a different population, which gives you a different kind of mean value of A. And if you kind of aggregate them together, then you end up with a distribution that's conditioned on the first 2 people, and voila, you actually have a sample from your posterior distribution. That's kind of the main idea. So the rest of the talk now is actually going to talk about how to do this part in practice. We'll touch a little bit on what the parameter is, but really you can just think of it as being the mean. So we'll talk about how to construct a predictive distribution to fill in the rest of the table now. In the paper with martingale posteriors, we coined this term called predictive resampling, but really it's just kind of multiple imputation, so to speak. The main kind of idea is that working with a big joint predictive is pretty hard. So Dave Finetti said we should work with the likelihood and prior. And in the recent predictive Bayesian methodology, we'd like to work with a sequence of 1 step ahead predictive densities. So let's denote P of I as the predictive density of a new data point given y1 to I. The key is that we need to have a predictive density for more than just the nth data point. We kind of need the full-blown sequence. And basically from a simple factorization, you can decompose this joint predictive density into a sequence of 1 step ahead predictives. This is just the chain rule. And what this actually implies is that you can do a sequential imputation type approach. So given a sequence of predictive densities, I can draw from this joint density by doing sequential imputation. So in this algorithm here, we have the outer loop, which is the number of posterior samples. So you can just ignore this. And in the inner loop is the bit where interesting things are happening. So what we're going to do is we're going to first draw a sample from our predictive density fit to the actual observed data, y1 to n. And the thing that's a bit funky is that we're going to actually update our predictive density, treating that new imputed data point as if it was a real observation. So all we've really done is moved one step ahead in the chain rule. You keep doing this onwards to some big capital N, and voila, you have a sample from this joint predictive density. So this update part is really just about getting this kind of conditioning to keep going. So suppose you picked N big enough, and you wanted to basically say that's your full population, you can then compute a parameter of interest, and that gives you a single posterior sample from your posterior distribution. So it might seem a little weird that this can actually be faster than MCMC, but we'll talk a little bit about that later on. So this inner loop here is to actually generate a single sample. So now we're going to go through a very easy to understand parametric example using a Gaussian model. We're going to talk about what this step looks like, which is easy, and what the updating step looks like, and what the final parameter looks like. And you're going to see, at least with some figures, that it actually indeed does correspond to posterior sampling. So here's the canonical example that we like to do. We work with the Gaussian location model, super standard. You just have Gaussian likelihood, variance 1, unknown parameter theta. And we're just going to stick to this kind of regular standard normal prior. Of course, it's conjugate, so you know that the posterior density looks like this, where the posterior will be centered at roughly the sample mean with this extra 1, and roughly the sample variance with this extra 1 as well. Of course, you can directly compute the posterior predictive density, which would then be a Gaussian centered at, again, this kind of regularized version of the sample mean. And then our variance will be the observation noise plus this little bit of extra kind of posterior uncertainty. But what we're going to do is we're going to turn this around. We're actually going to start with this guy as our model. We're just going to assume that we didn't kind of get to it through a posterior likelihood prior kind of argument. We're just going to say, okay, I'm just going to use normal distribution, and I have some insight that decides these are a good estimate for my parameter of interest. So to carry out predictive resampling, then the main idea is that obviously I'm going to draw a sample from this Gaussian. That's not difficult at all. Based on the estimated values, I'm just going to draw a new sample of yn plus 1. The thing that's a bit interesting is what updating does. So in this case, my predictive density has two parameters, just the mean and the variance. So I'm going to update the mean. I'm just going to treat this yn plus 1 as if it was a real data point. So the first n data points are real. The n plus 1 one is simulated. Then I need to update my counts, and I need to update my variance as well. And I'm going to keep doing this until some really large value of n, see where I end up, and repeat. So this is what predictive resampling looks like for an actual Bayesian posterior predictive model. So what this looks like in practice, I can do this as a simulation, and that's exactly what I've done here. So on the figure on the left here, I have trajectory plots of the population mean. So these are estimates, theta bar n. And on the x-axis, what I have is the number of samples I've imputed. So all of them are going to start at n equals to 10. That's the number of observations I actually saw. They're all going to start at a sample mean of 1.84. You can't see it, but it all starts there. And then what I'm going to do is I'm going to draw these Gaussian random variables using this type of predictive resampling algorithm. So obviously there's going to be a kind of knock-on effect where if I draw a small value, then I'm more likely to draw a small value, and it's going to keep going. So I can follow one of these trajectories, which is one imputation of the population. You can see it starts out wiggling like crazy, and it kind of stabilizes at this value here. So what's happening here is that I'm drawing more and more samples from my imputed population. So I'm getting kind of closer and closer to knowing theta infinity, so to speak. Basically, I'm filling in the population. And so that's what each of these trajectories looks like. The thing that's a bit unintuitive is that when you repeat from scratch this kind of predictive approach, so I start again at n equals to 10, you actually end up on a different trajectory. And that's because the first sample you draw might be larger or less than 1.84. And whether or not it's bigger or smaller then will determine kind of where your trajectory will end up. There's this kind of feedback loop system. So if you keep doing this many, many times and look at where all of these kind of curves end up, these are all estimates of the population mean, but they're random because you've imputed this new population. And you plot this on a histogram or a KDE, you can see that actually it overlays very, very closely to the known tractable posterior density, which is just the Gaussian from the previous slide. And you keep doing this for bigger and bigger samples, they'll overlap exactly. You can actually prove using Dup's theorem that indeed the distribution of the sample means will be exactly the posterior distribution. So there's no kind of ambiguity here. Okay, so if there's one kind of slide to take home, it'll be this one, that you can actually do this kind of funky bootstrap-like thing, look at the distribution of the mean at the end of the sample, and you actually get back the posterior. Like there's no ambiguity. It's theoretically true. So now that we're kind of equipped with this simple posterior predictive framework, what we want to do is, of course, we want to generalize. This is kind of the notion of post-Bayes. You take bits of Bayes that you like, and then you generalize by letting things be a little bit more relaxed. So we'll talk a little bit about the framework that we discussed in martingale posteriors, which is really just kind of a parametric focus. It's basically a special case of the quasi-Bayes framework that was introduced in the non-parametric setting. We'll talk a little bit about what the parameters are, just to kind of tie things back to chapter 1, and then we'll kind of tease some of the future chapters. So the main idea is kind of obvious that if I had a sequence of predictive densities, why be constrained to the sequence of posterior predictives? Can we just choose a more general one? So I'm now going to specify a sequence of predictives as my model. We're going to start with P of yn plus 1, given y1 to n, because there's no need to actually generate a predictive for your observations from before, but sometimes that's helpful as well. And our parameter of interest can be much more general. So I'll talk a little bit about what this guy is on the next slide. It'll be super familiar. Same thing as Gen Bayes. The neat thing is that you can actually specify your entire Bayesian model without a likelihood and even without a prior. This is the bit that's a little bit surprising. So we'll talk a little bit more about this later on. Unfortunately, your predictives can't be anything. At least in this framework, it needs to be a martingale, which is why there's this title. But we'll talk a little bit about what this means like in terms of kind of implications in practice later on. Then to do statistical Bayesian inference, there's two steps. You do the imputation step. So that's just sequentially imputing using your sequence of predictives. You fill in the rest of the population using your sequence of one step ahead predictives. You do it in this kind of sequential manner because you kind of need to feed this yn plus 1 back into the model to predict the next one. And you keep going on to infinity until you have y1 to infinity or some large approximation thereof. Notice that, of course, y1 to n is fixed. This is the observed sample. So only the n plus 1 onwards will be random. And then you just compute your parameter of interest because you've seen basically enough from the population. Voila, you have a sample. So we call the distribution of theta infinity the martingale posterior, which is kind of just really marketing. But it is just the posterior distribution, like by definition. This is just the construction. So parameter of interest, just kind of a quick word about how it's overlapping with Gen Bayes, but also how it's a little bit different. For IID samples from F0, you can usually define your parameter of interest in this kind of minimal expected loss kind of vibe. So this is exactly the same thing as Gen Bayes before. F0 is your unknown sampling distribution. And what we're doing here in the martingale posterior is we're just going to sub in F0 with basically the empirical distribution of the data that you've drawn. So we're just going to treat this F0, instead of using F0, we'll talk about the random empirical distribution of your imputed population. And of course, we have the kind of standard non-parametric choices like the median and the mean. You can also choose the negative log likelihood. So I think Jeremiah has worked on or talked about this in quite a bit. The main difference between this and Gen Bayes, however, is that your loss function is not actually going to be used at all to construct your predictive, at least not in the vanilla framework. It's sort of just a post-processing step. So your construction of the predictive has nothing to do with the parameter, which is maybe good, maybe bad. We can talk a little bit about that later on. But it sort of has this nice detachment of the data to the parameter, very much akin to what you would do for like a frequentist bootstrap. Like your model doesn't necessarily have anything to do with how you do the bootstrapping. So kind of to summarize then, there's two steps, right? You just impute from this big joint predictive. For now, we're going to construct it as a sequence of one step aheads because these guys are nice to work with, easy to interpret. I actually don't know yet if there are ways to do this more generally without doing a sequence of one step aheads or using kind of the Bayesian posterior, but that's sort of an open question. And now I'm basically just going to list out a couple of examples. Of course, when you use the predictive density as the posterior predictive and your parameter of interest is, say, the maximum likelihood estimate, you recover the Bayesian posterior. That's Dub's theorem, at least in the identifiable case. But we're going to generalize because this is a post-Bayesian talk. So what happens if I consider kind of more general predictives? I'm going to leave theta somewhat unspecified. The first one we're going to talk about is the empirical distribution, because the empirical distribution is really popular in frequentist statistics. And unsurprisingly, you recover something called the Bayesian bootstrap, which again has a really long and rich history. So this is not new methodology, but it's new, I would say, new interpretations of old methodology. Much more interesting is actually if you use a more general predictive. Unfortunately, I don't have time to go through all of the details today, but I'm going to kind of zoom through a couple of examples, and then Sandra and Lorenzo will kind of go into more details for the respective specific parts. So if there's a general predictive and we make it satisfy a martingale, we sometimes call it the martingale posterior, or depending on the choice of the predictive, also the quasi-Bayesian posterior. So we'll cover a few kind of parametric and non-parametric examples later to show that it is indeed more flexible, but it's not as flexible as you'd like, which is one of the open questions with respect to this kind of framework. So we mentioned that there are some kind of caveats, right? Like you can't just choose any predictive distribution. Unfortunately, I don't have time to go through the details, but luckily for you, in 2 weeks, we'll have one of the world experts, Sandra Fortini, talking about what the conditions the predictive distribution should satisfy. So you can also investigate what conditions the predictives do satisfy already for Bayes, and which ones of those you can relax. So in particular, we really like this martingale condition, which was sort of talked about actually a long time ago by a paper by Bertie et al. In 2004, but it wasn't really applied to this kind of framework. But in all three of the works that I introduced earlier on, we require this kind of martingale condition. But it's not strictly necessary, and there are different variants of this. But it's a really interesting kind of relaxation of exchangeability. If you're interested and you kind of want to peep ahead, I would highly recommend looking at this recent paper in Statistical Science by Sandra and Sonia. Like it's a fantastic summary of kind of the connections between prediction and Bayes. They kind of talk about as well what happens in Bayesian models. If you want to look at just the predictive and Bayesian models, it makes you really understand kind of how rich this connection is. But if you're a bit busy, then you can wait until Sandra's talk, which I think will be super exciting. I'm really, really looking forward to that. Unfortunately, we're just going to kind of sweep the theoretical stuff under the rug for now. Just talk a little bit about intuition for the predictives. There's also obviously many choices for the predictives, right? Like you have your data set y1 to n. How do I know if my predictives are going to be good? And Vic's going to talk a little bit about this, as well as how to obtain uncertainty in the model. So this is some new work that he did with Chris and Steven, and it's sort of pushing the boundaries on how much you can actually take this predictive Bayesian approach, moving past things like Bayes factors and marginal likelihoods. A lot of this is based on work by Phil David, as I mentioned before, as well as these strictly Popper scoring rules by Nighting and Raftery. But the kind of gist is that you can do everything with just the predictive, including model selection. Okay, so that's kind of teaser for what's going to come in the next few weeks. We're going to move a little bit back to the uncertainty case, and we're going to talk a little bit about the Bayesian bootstrap. So the Bayesian bootstrap is my favorite algorithm of all time. It's a little bit nerdy to say that, but it does really have some really interesting ties between Bayesian frequentism. And for me, like my whole life is basically now just spent to generalizing the Bayesian bootstrap, at least for the next few years. So how do we start? Well, we're going to start with the simplest non-parametric predictive, which is the empirical distribution. This is sort of very canonical in frequentist statistics. Why not do this in Bayes as well? So we'll basically just directly choose Pn as the empirical distribution. So this is the predictive given real observed samples. And we're going to see what happens when we do predictive resampling with this. So you repeat 2 steps, right? First, you draw a sample from the predictive, then you update your predictive, then you keep going. So what does this look like? Well, resampling from an empirical distribution is literally resampling, right? You just draw one of them at random. So you pick between the observed data, y1 to n, with probability 1 over n. Updating as well is pretty obvious because the empirical is just a sum. So you're just going to lump this guy back in, and you get a new empirical distribution. Of course, the thing to note here is that your samples of yn plus 1 will always be repeats of y1 to n. So if you keep doing this onto infinity, you're never going to draw kind of samples outside the original little n number of samples. Instead, you'll get kind of repeats of y1 to n. And the number of repeats will basically be random. So if you look at what the population converges to, so I'm just normalizing by the number of predictive resamples, but here, of course, the unique number of atoms here will always be up to little n. You'll basically get a randomly reweighted version of the original empirical distribution. And it turns out that the weights will be Dirichlet 1, 1, 1 because of this Pollier-Earn type argument. So it's not a coincidence that if you just choose your predictive to be the empirical, you'll actually end up with these funky looking Dirichlet weights. Now, this set of funky Dirichlet weights has a really long history. It's called the Bayesian bootstrap. It started roughly around Rubin in 1981, but has a much stronger history. Also is connected to these things like Dirichlet processes, but you can actually kind of come up with this directly by looking at the empirical distribution as your canonical choice of the predictive. So this is what it would look like. The martingale posterior, so to speak, is really just the Bayesian bootstrap when you use the empirical distribution. You draw n random Dirichlet weights, so it's kind of on the simplex. You reweight your data, you compute your parameter of interest. And now you can get a posterior on theta that's sort of entirely data-driven, so to speak, because you use the empirical distribution as your model. As a quick aside, there's some really nice properties under modeling specification. It's also really fast and parallelizable. So Harita is going to talk a little bit about applications of the Bayesian bootstrap in robust cases, but I'm not going to talk about that too much. The main thing I want to talk about is sort of the connection to the frequentist case. But before we do that, as promised, there's a little animation here. I made this during my PhD, so I try to reuse it whenever I can. Just to illustrate those who haven't seen the Bayesian bootstrap before, basically, instead of drawing multinomial weights, you draw these smooth Dirichlet weights. You reweight your data at random. If your parameter of interest is, say, the parameters in a linear regression, then you just compute kind of the weighted OLS, so to speak. You look at where the intercept and the slope is, and then you can plot this as a posterior distribution. And this is a proper kind of Bayesian non-parametric posterior distribution with some really nice properties. So why do I like the Bayesian bootstrap so much? Well, if you put it side by side with the frequentist bootstrap, it's sort of neat to see the real difference between the two. So the frequentist bootstrap actually looks pretty much the same. You start with the empirical distribution, but instead of drawing kind of this remainder, you draw y1 to n star. So you imagine another kind of sample of size little n, and then you compute your estimator on this sample. Whereas for the Bayesian, you again start with the empirical, but you actually draw the remainder, and then you compute the estimand, so theta as a function of y1 to infinity. So in a nutshell, then you could say that Bayesians consider uncertainty on yn plus 1 to infinity, and an estimand because you're computing it as a functional of the whole thing. Whereas the frequentist looks at uncertainty on y1 to n and on an estimator, the hat. So estimator here. And as Stephen Walker puts very nicely, why would you care about what you've seen already when you can actually think about what you've seen in the future? And I don't quite fully agree with that statement, but it sort of highlights that, at a moment's glance, you can argue that maybe Bayesian uncertainty makes more sense. It's talking about something you haven't seen yet, not about something you've already seen. So maybe we should try a little bit harder to do this. For me, the take-home message from this is that actually Bayes and frequentists are much more on equal footing than maybe we'd like to admit, because both methods only specify the empirical distribution. Both methods carry out some kind of resampling, and both methods compute theta. But nowhere kind of in this specification did I have to manually choose a pi of theta or even kind of talk about it, right? There's no prior here. There's no likelihood either. It's just a predicted. Of course, underlying this is the Dirichlet process, and you can kind of argue like that. But just just looking at it, you just have the empirical distribution. So it sort of highlights that actually the bit that changes between Bayes and frequentist is not necessarily the prior, but kind of the remainder of the population that you're talking about, which I think is kind of interesting. Okay, so that was a little bit of philosophy. We're going to talk now for the last 15 minutes or so about predictive models. What can you do with this, right? This is the most exciting part of post-Bayesian methodology. Can I actually do something new? And the answer is yes, but turns out it's really difficult, which is why I still have a job, I guess, as a researcher. We're going to start talking about parametric predictives first and then non-parametric predictives later on, even though these actually came first, technically. So in Holmes and Walker, which is like a follow-up paper in 2023, they advocated to use the plug-in parametric predictive density. This is also done in the recent review by Sandra and Sonia. And the main idea is that, okay, well, if I'm going to use the plug-in predictive as my density, then this can sort of replace my posterior predictive. I'm not going to mix over theta. Instead, I'm just going to plug in the value of theta. And if I see a new observation, well, I could fit the full kind of maximum likelihood thing, but I'm also going to be a bit lazy and just do stochastic gradient descent. So this is one step of stochastic gradient descent. Basically, I'm just adding to my old parameter one gradient step along the gradient of the score function. Here we've reweighted by basically the sample size, but you do want to be a little bit more careful here in practice. So all we've done is that we've replaced the posterior predictive density with the plug-in predictive density, and we've kind of advocated for a parametric model in this setting. And actually, you can show pretty quickly that under resampling, if I draw yi plus 1 from this model, then the score function will have mean 0. So it turns out this parameter will actually be the martingale instead of the predictive density. But this is just a technical note. The main thing that's interesting is that if you do this algorithm and you do predictive resampling under some assumptions, you can actually prove that the posterior exists and it has some really nice properties. And you can basically do prior-free parametric posteriors without MCMC. So I have an example on the next slide from some recent work with my collaborator, Andrew. So here's an example from a recent paper that I worked on with Andrew Yu, who's at Southampton now, one of my longtime collaborators. And we basically showed that we basically applied this previous algorithm to a student T regression model. So if your likelihood is a student T, then there's no conjugate prior. So your only choice is to do MCMC. So the model was relatively easy. The data set wasn't gigantic. So Bayes took about 2 minutes for MCMC. You can see in the black line, that's the Bayesian posterior for 2 of the coefficients that were non-zero. For the parametric martingale posterior, so to speak, we came up with a kind of way to do this using some nice asymptotic theory, which gives you the distribution in the dashed line. So it's sort of predictive resampling plus a little bit of noise. And this took about 0.03 seconds. So we didn't even kind of bother to optimize this. It was just so much faster. It was basically the same time as like a regular bootstrap. So it kind of shows that you can actually kind of get these really crazy computational gains. It's not general, but sometimes it does really work quite well. The main reason is because I can do things in parallel, and also these kind of computations, stochastic gradient descent is pretty darn fast. Some recent work in progress that I've been doing with my student is actually kind of doing the best of both worlds, where you do a mixture of this parametric predictive and the empirical distribution. So kind of in between the parametric and the non-parametric Bayesian bootstrap, so to speak. Turns out the theory for this is a little bit more tricky. You have to think a little bit delicately about how to show things actually converge, but you get kind of somewhere in between the two in terms of posterior inference. For the non-parametric recursive updates, I think this is actually where maybe the martingale posterior framework has some really nice contributions, because in this case, in BNP at least, for Bayesian non-parametrics, it tends to be a little bit difficult to elicit good priors because you're talking about things like densities or functions. And not only is it a bit hard to do the prior elicitation, computation is also usually like completely insane. Another way to think about this is that the Bayesian bootstrap doesn't quite do enough, right? It's only discrete. So if I was interested in something, say, that has a density or something that's smooth, like a function, then how do I do that? So part of the work that we were working on was actually kind of repurposing old methodology to do posterior inference, specifically focused around methods that were kind of recursive, so to speak. So you have your old predictive density, you see a new data point, how do you kind of update them locally so you get a new predictive density? So Lorenzo is going to talk a lot about this methodology because he worked on this during his PhD, got a lot of really cool ideas around how to do this. Today, we're just going to give you one kind of canonical example to show you that actually this is more general than regular Bayes, because this kind of stuff you can't really do using a traditional likelihood and a prior framework. And basically what we're going to do is we're going to use a kernel density estimate. So just a little bit of reference here. These are some examples of methods that we've kind of repurposed. So Sonia and Sandra repurposed this method from Newton and Rattree in 1994, and we repurposed this method from Han et al. Basically, both are based on Bayesian models, so not quite fully non-Bayesian, so to speak. But just a quick illustration here. Here's an example of a methodology that we looked at in our paper, which is completely kind of free of a likelihood and a prior. It's just basically a kernel density estimate. So here I have my new predictive density is going to be a weighted sum of my old density and a kernel. Right? This is just a kernel function centered at my new data point yi plus 1 that I'm kind of updating. So in this figure here, you basically see the old density in gray dashed line. The new data point is this black dot, and this copula kernel, this k function, is this solid line here. And you can see as I change the bandwidth of this copula kernel, I get this blob that's more and more peaked. And then when I update the predictive density, I just take a mixture of those two things, right? I mix this guy with this guy, and I get this new kind of squiggly looking density that has a little bump here. It really is basically a kernel density estimate, like nothing fancy. Of course, we use something a little bit more complicated than the regular Gaussian kernel. We kind of have to use these copulas to ensure that it's a martingale, but otherwise it's basically just a kernel density estimate. You can actually extend this as well to conditional density estimate. So you get something like a Nadaraya-Watson estimator. So this model is purely like driven by data, essentially. Like there isn't really a prior except for P0. The copula kernel is inspired by Bayesian non-parametrics, but I don't talk about a likelihood or a prior here. It's just a recursive kernel density estimate. And what's neat is that you can actually get posteriors that look very similar to a full kind of Bayesian non-parametric construction. So on the figure on the right here, we have the traditional Dirichlet process mixture model. If you're not familiar with it, it's basically an infinite kind of Gaussian mixture model. To sample, you have to do pretty expensive Gibbs sampling, but actually this is already a really fast implementation. It took around 25 seconds for my little data set here. You can see that I have a posterior mean density with some nice credible intervals, 95% credible intervals for the density. On the left here, we have basically applying this kernel density estimate update exactly to the same data set. So you fit it using the same update, and then you kind of keep going and impute the remainder of the population and look at what random density you get. So the black line is the posterior mean, and these gray intervals are the credible intervals. And okay, they're not exactly the same, right? They're a little bit wider here and a little bit narrower here, but they're pretty comparable. The difference is that the first one required MCMC in 25 seconds. The second one took about 10 times less time and didn't need MCMC. So it was all very kind of standard linear algebra computations. But for me, I thought this was really interesting that you can get full-blown Bayesian non-parametric posteriors without actually needing to A, construct a likelihood in a prior, and B, even do any kind of Monte Carlo, like Markov chain Monte Carlo. It's just regular vanilla Monte Carlo. We've also done kind of some recent work which looks at extending this. So far, I've spoken a lot about predictive densities and predictive models, but there's this kind of craze with these generative models these days. And indeed, you can actually think about generative predictives as well. It has a really nice tie to quantiles. So if you consider a more general predictive, instead of actually trying to estimate the predictive density, I'm going to estimate kind of a sampler. Qn is going to be a function which takes as input a random variable between 0 and 1. Just going to use a uniform random variable here. I'm going to plug it in, and that's going to give me a random y. and I'm going to have a recursive update for this kind of generative sampler. It turns out, of course, this is very similar to a quantile function. It's not exactly a quantile function, but you can kind of imagine it as such. So we've kind of aptly named this as the quantile martingale posterior. And you can actually derive some nice theory that shows that the posterior exists. It has some really nice properties. You can even sample from it approximately. And you deal with some really nice kind of properties. But of course, this is kind of a toy example. Like it would be really nice if I could do this more generally. So far, we've only really gotten this to work for a pretty simple one-dimensional quantile estimator. But it goes to show that maybe the predictive framework is more general, right? Like maybe we'll be able to one day use one of these complicated generative models. So on that kind of positive note, I'd like to conclude and talk a little bit about summarizing the predictive Bayesian framework, as well as some of the open questions that I have at least, but I'd also like to hear kind of what open questions you might have. So in summary, basically Bayesian inference is about imputing. So it's about imputation of this remainder of the population. This is not really a new idea, but it's been revitalized recently because we've actually been able to do this in practice without going through the likelihood and the prior. The bootstrap interpretation, I think, is quite interesting. Of course, underlying it is still a Bayesian model, so it's not quite fair to say there's no prior, but at least I didn't have to choose the prior. And in terms of methodology, I think it's still kind of an open question. You can specify the model directly, and in some cases, it's really helpful. So in particular, when you have no prior information on your parameter of interest, or you have no prior information on, say, the density or the function, then maybe the predictive approach is a good way to go. If you actually have prior information, it's actually kind of difficult to get it back in to the martingale posterior. So this is some work that I'm doing with one of my PhD students. So we can generalize Bayes to this. It's kind of an orthogonal generalization compared to Gen Bayes. We move kind of completely away from measures on theta and instead talk about measures on the predictive density. Of course, what's most interesting is what this means in practice. So there are some strengths that I think are modest but noticeable. The first is that you can actually get exact posterior sampling. I say almost because you need to sometimes do a truncation, but the kind of damage that that does is much less than MCMC. It couldn't offer potentially really large computational speeds up. It's potential because it's not always the case. But at least in most of the examples I've seen, we get kind of 10 to 100 times faster speed up on the same compute without any kind of parallelization. I mean, the main idea is that you don't have to do MCMC because that's not the way you do Bayes rule. Instead, you do Bayes rule using the predictive. The interesting part is that you can sometimes do Bayesian inference without explicitly specifying a prior. In fact, for the parametric cases, you can even show that the posterior mean is exactly the same as the frequentist point estimate. So there really is no prior there at all, actually. And in some cases, it can be more robust to model misspecification, but not always. So the Bayesian bootstrap, for example, is an example where it's really interesting because you can get posterior inference on parameters that kind of index a model, but not have to assume it's true. But in the parametric case, for example, you're actually less robust to model's misspecification. You have more flexibility, so there's kind of a lot you can do with it. It's still sort of an open question here. So I'm going to be talking about this in the upcoming satellite workshop at BayesConf, some of my speculative thoughts. I think the weaknesses are more interesting because it sort of shows how much you take for granted when you do Bayesian inference. Like the fact that you build your model with the likelihood and prior actually is really helpful because there are all these things that you don't have to deal with. The first is that this pesky martingale condition is restrictive. It's not obvious that it's needed, but if you try to prove that the posterior even exists, you're going to immediately face some trouble unless you have some kind of martingale condition. And your performance will also be really bad because you'll end up getting biased estimates of the parameter or the density. So it is sort of necessary, but the question is whether or not you can relax it. And I guess this is sort of the stepping stone to incorporating real machine learning models. So far, all the models we've done have just been kind of standard predictive Bayesian models. It's been pretty difficult actually to extend it. Working on some ideas, but again, it's not that easy. This martingale condition is automatically taken care of when you do the Bayesian likelihood and prior. It's already there. You never have to worry about it. The second point, which is really a pain point for general Bayes in general, but is also a pain point for our case, is how to incorporate any notions of structure into the predictive. So things like hierarchy, which I'm working on with the student, things like dependence, even time series. Like it's not really that easy to come up with a good predictive without going through the likelihood prior machinery. So in one of the discussions for our paper, Stefan Lawrence aptly put that it's cool that you can do this without the likelihood and prior, but so far it seems like you're always using the likelihood and prior to come up with it in the first place. And he's correct. Like it's really hard to come up with like a structure, but you don't have to worry about this when you have your likelihood and your prior, right? You just multiply things together. So it's sort of still an open question, I think. I have some hopes around hierarchy and dependence, but kind of having a full-blown Gen Bayes, post Bayes kind of for dependent data, I still don't know yet. And this is actually something Jeremiah and I are talking about a lot, like how to kind of bring Gen Bayes into structured models. Really hard. The final point is more for those who are interested in theory, but in general, theoretical properties are at least I found them to be harder. Maybe I'm just not good at math, but we've been able to show things like the posterior exists, things like consistency, and a little bit of posterior contraction, but only for specific models. Something kind of general, like we have all these tools for Bayesian non-parametrics, can't be used at all, at least not to my knowledge. So it turns out kind of theoretical properties are a little bit more hairy. In fact, whenever I write a paper related to this, I have to first show that the posterior even exists, which is not a concern that you have when you're going through Bayes. So sort of in a nutshell, you get these nice perks for relaxing the Bayesian framework, but you also actually lose a lot. And I think Sandra will talk a little bit more about kind of what structure is just enough that you still have this kind of Bayesian type flavor in the next session. Okay, so luckily not super over time, so thank you so much for your time, and I'm happy to take any questions now or offline.
Thank you so much, Edwin. Um, if anybody does have questions, then feel free to raise your hands or put them in the chat. Maybe if there is none immediately, I might quickly sneak one in, if that's all right. Um, so on this idea that uncertainty, the source of uncertainty arises from the data we haven't seen yet, is there a connection then between the flavor of functionals we can consider as parameters and the conditions we need on a loss for posterior concentration in Gen Bayes insofar as we need data to be the only source of uncertainty? Like,
It's a really good
I
question. Yeah.
need, like, thinking about the hierarchy or how to say this, communicating structure in models, and many hierarchical models I can think of where data are not the only source of uncertainty. Is this
It's a
part of the problem?
It's a really good question. So this is directly related to identifiability. So it's sort of implicit there in Dub's theorem that the parameter needs to be identifiable. Kind of more mathematically, it's sometimes like it needs to be a measurable function. Here's an example, actually, what you just mentioned. So if you're doing hierarchical modeling and you want to do, say, a global parameter of interest, so something like a population mean, you don't actually need to fill in all of the groups. You only need one sample per group, and that's actually already enough. So it's exactly correct that parameters which basically have no uncertainty left when you fill it in with enough data. I think Phil David called them external parameters or extrinsic parameters or something like that. That's in contrast to parameters that are kind of helping you model things. So maybe like weights in a neural net. You never expect that kind of posterior to collapse to Dirac. For me, this is really nice because it makes me think about the difference between like a real parameter that I can one day estimate if I had enough data versus these kind of internal weird ones that don't mean anything, like the weights in the neural net. So for example, this predictive might have loads of parameters, but they don't really mean anything. They're just there as vehicles. So yeah, completely actually, like this notion of parameters being functionals also means that you really need to be super honest about what you're trying to estimate. So if you have a posterior that doesn't concentrate, then maybe your question is sort of ill-posed statistically. I don't fully agree with that kind of sentiment, but some like Stephen, for example, says like if there is no data that I can fill in to estimate theta with no uncertainty, then that's a bad theta to estimate. I'm not sure if that's what I agree with, but I can see the sentiment. It makes me really think about what you want to know when you're doing inference. It's sort of hard because in Bayes there's no ambiguity, right? It's just a posterior. Who cares, right? Like it's a random variable. I don't know if that answered your question.
I,
Got to
I think it
ramble
is,
a
but I
bit
think it
about.
also it's given me another one as well, if that's all right. I mean, if
Yeah, of
if
course. Yeah,
the idea that you would want to separate between these like um does Diffinetti call them metaphysical parameters
yeah, yeah.
and notions of parameters that, as you say, okay, well, let's just say we could estimate given infinite data. In the same way that maybe we want a framework which is able to infer one but not the other, and you were talking about incorporating priors, is there also some argument here to be made that we would only want to put priors on the things that we could eventually estimate?
Yes, that's a good question because you have this concept of you want the prior to wash away, so to speak, with more and more data, right? Is that what you mean? Like you do want the prior to be on something that will eventually be recoverable. It's not usually.
I think I probably meant more something along the lines of maybe we want to put a prior on something which we can tangibly elicit.
Yeah, I mean, I think that's sort of in line with this view of writing Bayes out in this push forward way, right? Like you say, this is the theta that you want. even in Gen Bayes, right? You say this is the theta that you want, which minimizes this loss function. It doesn't really make sense to put, okay, so this is obviously just a bit kind of heated, but putting priors on weights in a neural net, for example, I find that quite challenging, right? Because it doesn't achieve the same purpose, right? You put the prior so you get good mixing. Not the same thing as putting like a careful prior on a location, which is also one of the issues with non-parametrics, right? You put a prior on the density. What does that mean, right? Like how can I even think about my subjective uncertainty on the density? I can think about my subjective uncertainty on the mean of the density, but for the whole density, like I'm not really sure. So yeah, I agree with you that basically I don't really think priors on these big objects that are really hard to think about if they're even recoverable in the infinite data limit like makes sense. I think you want to kind of stick to small things, which is sort of the direction that I'm pushing the work now, which is towards kind of more careful prior. Like I want to put the prior back in basically. Like Azan, you know that I'm actually a big fan of priors these days. A little bit of a comeback. It's precisely because of this. Like there are things that you can never recover, right? Like weights in a neural net. Sometimes even like the full regression function, so to speak. But there are things that you would hopefully like to recover, like the mean or an average treatment effect. And I think you do need to talk about them separately. So I'm kind of very much pro like priors on small things, and you kind of let the data do the rest, so to speak. Hopefully the martingale type framework is part of the way there, right? It lets you at least do it without the prior at all, which is nice.
No, it's super cool. Thank you. Does anybody else have anything they'd like to ask Edwin while we have him? Yes, Yanis?
Hi, thank you for the talk. I just wanted to ask, you showed this one work where you use kind of stochastic gradient descent to get update the predictive distribution.
Mhm.
But I was kind of that's kind of seems like it would be something that would be applied to like a machine learning model where you usually use stochastic gradient descent. So in that context, which parameter would actually be worth estimating would be kind of my question. Because
Really,
kind of in a Bayesian machine learning context, the whole goal of doing Bayes is usually to get a predictive distribution in the end. So if you start with like the MLE plugin predictive distribution, what is the actual goal at the end?
yeah, that's a really good point actually. So that sort of highlights the difference, I guess, because like you said, the goal is really to get the posterior predictive, not to get
Yeah.
the uncertainty. I'm not sure you would actually gain anything if you say use the parametric predictive update rule for stochastic gradient descent. You'll get this random weight. I mean, you could average over it. I don't know what happens actually. Maybe that's something to try.
Yeah.
Um,
Would that be better than the MLE? I don't know.
there is some evidence to suggest that if you use, so you have the plugin predictive as your first one, but you kind of
Mhm.
have this extra one on top, which is the mixture of the plugin when you average over your whatever posterior. So Jeremiah and I are actually thinking a little bit about whether or not that's helpful. I don't know though.
Okay.
It sort of highlights why it's kind of hard, right? Like you try to do gradient descent on the weights, but what do you actually gain in terms of prediction? I'm not really sure yet. So sorry, it's a bit of a negative answer. I don't know. I want to try
Okay.
actually. Let me know if you find out.
Well, thank you. We maybe have time for one very quick question. Um, and if not, then maybe just to say thank you very much again, Edwin, for starting us off so strongly on chapter two. And we'll be back in a couple of weeks' time.
Yeah, thank you so much for attending. We'll see you in 2 weeks with where Sandra gives a really cool talk. I'm really looking forward to it. So, bye.
Bye, everyone.